Hello and welcome. Ansys Fluent is a powerful and versatile CFD software which is widely used in the industry and academia. Engineers routinely use CFD simulations to test their ideas and optimize the performance of devices and processes. Usually, this results in a large number of complex simulations which consume enormous amounts of time. It is imperative to have these simulation times reduced because this will ultimately reduce the time to market. The traditional approach for this is to run the CFD solver on a large number of CPUs, otherwise known as high-performance computing. In recent years, we have seen quantum leaps in the development of GPU hardware and dedicated programming languages that help developers architect CFD solvers equivalent to those designed for traditional CPUs, but instead leveraging the power of the GPU. Ansys has been a trailblazer in the use of GPU technology for simulation and has taken this to a new level with the full release of the multi-GPU solver in Ansys Fluent. In this video lesson, through a simulation example of external airflow over a generic drone geometry, we will highlight the solver features available on the new Ansys Fluent multi-GPU solver. Excited? Let's get started. GPUs are well suited for parallel computing since they can perform many calculations simultaneously and process large amounts of data much quicker than CPUs. Leveraging GPUs in the CFD world is not a new concept, and GPUs have been used as CFD accelerators for quite some time. Ansys Fluent implemented offloading to GPUs technology in 2014 by passing some parts of the CFD solver algorithm to GPUs to accelerate the overall solution time. The local acceleration obtained was case dependent, and as the Ansys Fluent solver was not yet optimized for GPUs, this limited the overall solution speed up. Starting with the 2022 R1, Ansys Fluent takes this usage of GPU technology to a new level with the introduction of a new native multi-GPU Fluent solver. This new solver has been architected from the ground up to run natively on GPUs and exploit their full potential. This eliminates the overhead of exchanging the data between the CPU and GPU, hence resulting in faster simulation compared to offloading. Native GPU implementation results in astounding gains, and the main benefits include increased performance, reduced hardware costs, and reduced power consumption. The multi-GPU solver supports all mesh types and is available for all incompressible and subsonic compressible flows. It also supports temperature-dependent material property definition as well as turbulence models, solid conduction, conjugate heat transfer, moving walls, species transport, and porous media. In this video lesson, we will highlight some of the solver features supported by multi-GPU in the 2023 R1 version of Ansys Fluent through a simulation example of external airflow over a generic drone geometry. Before we proceed with setting up the problem, let's briefly understand the computational model being used. The model consists of a drone with 4 rotors. The rotational speed of the rotors will be set to 12,000 RPM for this simulation. The computational domain is entirely a fluid domain, and the drone mesh consists of 6 cell zones. 4 of these cell zones envelop each rotor. The next zone is the near field which surrounds the entire drone. Finally, there is the environment, which is a big spherical zone which represents the surrounding air. The cell zones are necessary to control mesh sizes and to accurately define the problem in Fluent. In this demo, we will first perform a steady-state simulation using multiple reference frame model followed by transient simulation using the sliding mesh technique. First, Let's open the Fluent launcher and select the solution mode. We'll be using the 2023 R1 version. The Fluent GPU solver is only available at the enterprise licensing level, and therefore select Enterprise from the capability level drop-down list. You'll notice that the native GPU solver option is activated under the solver options. To enable the GPU solver, simply check the native GPU solver option and click OK on the pop-up message display. Note that Fluent GPU solver only supports NVIDIA GPUs which are compatible with CUDA version 11 or newer. If your machine has a graphics card with more than one GPU and you intend to use the solver with multiple GPUs, then you'll have to set the number of GPUs you want to use. In this case, we only have one GPU available. When using Fluent GPU solver, the CPU processes are only used for case setup and post-processing, while the solver calculations are done by the GPU. You can increase the number of CPU processes to use multiple CPU processes in parallel during case setup and post-processing. Please note that the number of CPU processes specified must be greater than or equal to the number of GPUs specified. After the Fluent launcher is set up appropriately with all the inputs, click Start to open the Ansys Fluent GPU solver. Although the graphical user interface of the Fluent GPU solver is similar to that of the CPU solver, it is important to note that solver features not yet supported by the GPU solver will not be available in the GUI. Once Fluent is open, let's load the mesh file into the session. Go to File, Read, Mesh and select the provided mesh file. You can display the mesh using the Mesh Display dialog box. Notice in the solver settings that only the pressure-based type of solver and absolute velocity formulation are available in the GPU solver. However, we can solve both steady and transient simulation in GPU solver. Select steady as we will first obtain the steady state solution and then use it to initialize the transient run. Next, let's set up the physics of the problem. To specify the viscous model, select Viscous under the Models section. The turbulence models available to choose from are laminar, K-epsilon, K-omega SST, K-omega GECO and large eddy simulation. We will retain the default setting of SST K-omega model and click OK. Apart from modeling heat transfer and turbulence, the GPU solver allows modeling of species transport without reactions. As mentioned earlier, other models have been grayed out as they are currently not supported by the GPU solver. Since air is the only material required in this simulation, we will not define any new materials as air is available by default. The Properties section of the Create/Edit Materials dialog box has options to modify the properties of the materials. To modify the property, select the appropriate setting from the drop-down settings list associated with that property. The drop-down list will list the settings that are supported by the Fluent GPU solver. Currently, the property definition settings available in a GPU solver are fewer in comparison to those available in a CPU drive solver. Click Close to exit the Create Edit Materials dialog box. We will now define the cell zones conditions. There are 6 fluid regions that we previously discussed and all of them will have air as the assigned material. For the initial steady state simulation, we will define the rotation of the rotors using the moving reference frame method. To do this, we will check the frame motion box which will reveal new input fields. For rotor 1, we will set the rotation axis origin, the rotation axis direction and a rotational velocity of -12,000 revolutions per minute. For the other rotor regions, check the frame motion box and input the values as shown on the screen. Before defining the boundary conditions, we will create mesh interfaces. This can be accomplished by right-clicking on Mesh Interfaces in the Outline view and selecting Auto Create. To define the boundary conditions, open the Boundary Conditions task page and group the boundary faces by zone type. Go to the outer boundary in Outlet group and ensure that it is set to Pressure Outlet. Open the Pressure Outlet dialog box for the outer boundary and change the turbulent intensity to 1% and turbulent viscosity ratio to 1. Retain the zero gauge pressure and close the dialog box. Ensure all the wall type boundaries are set to stationary wall with no slip condition. Now we will set up the solution methods. By default, the simple scheme is used for pressure velocity coupling. In the GPU solver, only simple and simplex pressure velocity coupling schemes are available. Also, note that the pseudo time step method is not yet available for the GPU solver. To monitor conversions, we will retain the default settings of the residual monitors. We will also create a report definition to monitor the change in a target variable value as the iterations progress. In our case, let's create a report definition of lift force generated by the rotors. For that, in Reports group under Solutions tab, go to Report Definitions, New, Force Report, Lift. Here, select all the 4 propeller surfaces, namely Propeller 1, Propeller 2, Propeller 3 and Propeller 4. Check per zone to ensure we can observe the lift of each propeller separately. Select Lift Force under Report Output Type. Check Report Plot and Report File. Give a suitable name and click OK. For initializing the solution, select the hybrid method and click on Initialize. Please note that GPU solver supports both hybrid and standard initialization. Before running the simulation, let's save this case through File, Write, Case and Data as our setup for steady state is completed. In the Run Calculation group, set the number of iterations to 2000 and hit Calculate to begin the solution. The total simulation time will depend on the number of GPUs being utilized. The simulation is now complete. Looking at the report monitor, we can see that the lift report plot suggests that the lift value has been stabilized as the iterations goes on, indicating solution conversions. We can post-process this case similar to what we do with a standard CPU case to understand the results, but since the intent is to continue onto a transient simulation, let's go ahead. Now that we are finished with the steady state simulation, we will set up the problem for the transient run. We will run the transient case in 2 stages. In the first stage, we will run the case for a certain number of time steps to purge the initial transients from the computational domain. Once statistical steadiness is achieved, usually indicated by the periodic behavior of report plots such as lift force, we will run more time steps to save the data and record files for creating solution animations to visualize the flow fields. First, let's change the solver settings in the Physics tab from steady to transient. In the Viscous Model dialog box, check SBES for Scale Resolving Simulation option and click OK. We will assign the rotation to the rotors by imposing sliding mesh motion to each of the rotor cell zones. Sliding mesh feature is provided as a beta feature in the GPU solver of Ansys Fluent 2023 R1. The quicker approach to this is to go to the Cell Zones task page and click on Copy to the Mesh Motion in each of the rotor cell zone dialog box. This will copy the settings specified previously for the frame motion method to the mesh motion method. Notice that the check mark changes from frame motion to mesh motion. Do these changes for all the rotor cell zones. Since we have switched from a steady to a transient solver setting, ensure that the settings of lift report definition are correct and make any updates if necessary. In the Edit Report File dialog box, we can specify the storage location. In the Solution Methods task page, change the transient formulation to second order implicit. The time step size determined is based on two considerations. First, the step size should be such that there are 20 time steps between each rotor revolution. Second, to have cell convective current number less than 1 in the regions where turbulence is resolved in the computational domain. In this case, it is the region around and below the drone where the flow is turbulent. So, we will set our time step size to be 0.001 seconds. And for this first stage of transient analysis, we will solve it for 200 time steps. Also change the value of max iterations per time step to 30 in the run calculation task page. Save this case and data and run the simulation. Let's have a look at the lift report plot. We can see that the initial transients has died down and a statistically steady periodic pattern is achieved. We will now set up the case to create animation of airflow around the drone. We will be creating two animations. One will display vorticity magnitude and the other velocity contour in the Z plane. First, let's create an ISO surface of constant velocity. In the Results tab, go to Create ISO Surface. Select Velocity from Surface of Constant drop-down list and under Velocity, select Q Criteria Normalized. Click on Compute. To create this ISO surface from all the regions in the domain, select all the zones in the From Zones panel. Provide a value of 200K in the ISO values input field. Enter a suitable name for the ISO surface if required and hit Create to create the ISO surface. The ISO surface created covers the drone entirely and hence you will clip a small portion of this surface to make the drone relatively more visible in the animation. For this, go to Create, ISO Clip and select the ISO surface in the Clip Surface panel. Select clip values of Mesh, Y coordinate and click on Compute. Change the max value to 0.02 meters. This will clip those portions of ISO surface that fall outside the specified range. Provide a suitable name and click on Create. To display the drone along with the contours in the animation, we will create a mesh object. Go to Mesh, New in the Graphics group. Select Propeller 1, Propeller 2, Propeller 3, Propeller 4 and drone body from the surfaces. We will also apply colors to them by coloring by surface. We will apply different colors to the propellers and drone body as shown. Provide a suitable name to the mesh object and click on Save/Display. Now we will create a contour of vorticity magnitude on the ISO clip that we just created. Select vorticity magnitude under Contours of Velocity and uncheck Auto Range option. This should result in Clip to Range option getting checked. Enter the min and max values as shown. We will hide the color map display in the color map options. Select our clipped ISO surface from the Surfaces panel. Enter a suitable name for the contour and click on Save/Display. We will now combine the mesh object and the vorticity magnitude contour to create a scene which Fluent will save every specified time step to be used in the animation. Right click on Scene in the outline view and click on New. Select only the drone mesh object and vorticity magnitude contour on the clipped ISO surface from the list of graphics object. provide a suitable name to the scene and click on Save/Display. Finally, to create an animation definition, right-click on Solution Animations under Solution in the Outline view and click on New. In the Animation Definition dialog box, select the vorticity magnitude scene we just created. We will be recording this scene after every 5 timestamps. Specify the storage directory, provide a suitable name for the animation definition and click OK. This concludes the animation setup for vorticity magnitude contour. Similarly, we can set up the animation for velocity contour. We will skim through the steps quickly as they are similar to what we did previously. We will begin with clipping the z-plane to x coordinate values from -0.75 meters to 0.75 meters. We will then further clip the resulting surface to y coordinate values from -1 meter to 0.3 meters. Display velocity magnitude contours on the double iso clipped z-plane with velocity magnitude values ranging from 0 meter per second to 60 meter per second. Create a scene by combining the drone mesh object and the velocity magnitude contour. Finally, create an animation definition using this created scene and record it after every 5 timestamps. It is recommended to save the case and data at this point. Enter the number of timestamps as 260 and calculate the solution. Here, we have the final case and data after the completion of calculation. We should also be having 52.hsf files and a .cxa file generated during the calculation. To generate the animation of vorticity magnitude, open Playback under Animations in the Outline view. Here, we will read the .cxa file of the vorticity magnitude animation, which will be seen in the animation sequences list. Change the write record format to video file. In the video options, ensure the format is MP4 and change the FPS to 10. Also, we will change the resolution to 1920 by 1080. Uncheck the Use Stored View and change the orientation of the scene to a view that you would like to be displayed in the animation video. Once decided, click Write to write the video file. The animation video for the velocity contour can be created in the same fashion, and this is how both the animation videos look like. To summarize, in this video, we looked at the capability recently added to Ansys Fluent, which is the native multi-GPU solver. It has significant benefits over CPU-driven solver, which includes substantial reduction in simulation times and hardware costs. Using a simulation example of airflow around a generic drone, we learned about the Fluent features supported by the GPU solver. More and more features will be supported by the GPU solver in future releases. With this, let's wrap up this lesson.